excited today to introduce our speaker, Dr. Tomonari Saito. Dr. Saito came to Oak Ridge National Laboratories as a postdoc in 2010, and then became converted to staff member in 2012. And in a short time, he's now risen to the level of distinguished R&D staff member at Oak Ridge National Laboratories. He's also joint faculty member at University of Tennessee at the Bredesen Center, I guess. Dr. Sokolov is a member of Alexei Sokolov's soft materials group at ORNL. He is a synthetic polymer chemist. He has extensive experience in synthesis and in various applications of well-defined polymers. He currently leads various polymer science projects at ORNL, including polymer upcycling, Ventremer composites, self-healing materials, building materials, polymer electrolytes for lithium-ion batteries, fuel cells, and flow batteries. So he does it all. He has published more than 130 papers, peer-reviewed articles, received 14 issued patents, and has won R&D 100 awards in 2012, 2016, 2019, and 2021. He has received several awards, including 2 recent ORNL awards, and is Patel's 2023 ORNL Inventor of the Year. So today, he will tell you about some of his work on polymer upcycling. The title of his talk is Toward Closed Loop Circularity of Plastics by Chemical Upcycling. Dr. Saito.
Okay. Thank you very much. Well, thank you for the invitations, and hopefully you can learn something from what we do. So I'm going to talk about polymer in plastic, pretty much plastic recycling. So that's what we are doing. I'm going to highlight several of our work, but I will start with background. Okay, thanks for the introductions, and I think I can start from covering, but maybe you can. So plastics are you use every day, almost for sure. Everybody here use every day. So, for example, all of the maybe containers, could be Ziploc bag too, pretty common plastic materials. Water bottle, that's pretty common. Tire, that's all plastics. And also medicals. Medicals are quite important plastic usage because nicely sanitizing those things tend to be more single use, but that's a good usage of plastic too. So we use daily for sure the plastics. So maybe I think it has to be on there. All right. So just to general, so history of plastics. So the historically, some of the natural materials. So the natural polymer, of course, exists, but some of the more related to kind of human intervene is for example, natural rubber. That's archaeologically 1600 BC. That's some record there. But then the Charles Goodyear, he invented this patent 1839, vulcanizations. So this natural rubber, typical polyisoprene, it's actually need to cross-link it, make like tires or things. So that's later on industrialized this technique. So that's probably one of the first examples, although it didn't make everything from synthetically, but that's something invented there. Then the 1907, this is the first synthetic plastic product, bakelite. So this is the bakelite telephone, bakelite radio, those things was common back in those days. This is phenol formaldehyde resin. Still we use this chemistry. So for example, wood, this kind of chemistry still used right now. So that's in the first example of synthetic plastic materials. Then Carol does. So he is in DuPont. He invented nylon. It's a cover in there, but you can So he invented nylon 1935, and nylon is quite strong materials, can be used in net, ropes, those things. In World War II, that was used for parachute materials. So before that, I read it, actually that was using silk, but mass producing silk is not easy. That was changing many things. Unfortunately, he passed away right after 1937, he passed away. But yeah, this was widely, even nylon we use a lot. So that's the historic age. And people here maybe know, I don't know, people online, some of the internet may not know, the movie The Graduate, actually this person, I don't know the name, but said one word, plastics, as a future of direction. So that's back in 1967. So that's prediction is correct. I will show you the next slide and the production of plastics. Actually, next slide. So other things we do at the Oak Ridge, we relate to energy. So clean energy applications, we use polymer plastic everywhere actually. Either energy storage, it could be the fuel cell, could be the battery, many components, not everything made of plastic, but each important component is actually used in plastics. Also separations. So this just picture example is the desalination. This is water separation, desalination plant in Israel. But you can see the scale. These are all plastic-based membranes. And this is also industrial separation, like gas separation, those things, those also tend to be membrane too. Other things, structural materials could be composite for the car, those things, but also wind turbine blade, this massive structure, that's a plastic composite. So these polymers of plastics, these are quite unique and also very useful materials for these many applications. Okay, so this is on the left-hand side, you see the production plastics. Again, the movie, The Graduate, was made 1967. That's correct. So this trend was correct, right? So this we make now 400 million metric tons. That's a lot. This global. So actually, it's probably a little bit more. This is statistics now 2015. Right now, it's probably a little bit more. What's the challenge? Challenge is very useful, but not much recycled. Right now, globally about 9%. So this is some of the good reviews. So this is circularity is not there. Typically, most of plastic, unfortunately, is single use. So that's a challenge. Okay, so typical recycling. Recycling code 1 to typically 7. So these are common plastics, either PET, high density polyethylene, polyvinyl. Vinyl chloride actually right now they don't have a way to recycle. But these categorized one is majority of actually plastic currently we use. But if you look at on the bottom, this is how much recycled. It's not much. One of the challenges actually to mechanical recycle, it has to be very, very clean, no contaminant, nothing. Then they can recycle, but there's a lot of challenge associated with it. So we like to change that, and we like to enhance the plastic recycling. So that's what we are trying to do. Okay, so why it's difficult? One of the difficulty comes from mixed. Again, when I said so, right now current technology, if you have mixture of plastics, almost impossible. It's not easy to do it. This is still exaggerated picture on the right, but again, if you have this kind of mixture, this case is a little bit more some polluting the environment, but after this, it's pretty difficult to recycle from here. And economically, about $100 billion a year a loss. Since if they could recycle it, that's to change it. But also, it's to produce plastics has high the greenhouse gas emissions and also energy input. So this is relevant for the not only climate change, but also the energy usage and the global economy as well. Again, as I mentioned, it's mixture. Many of the plastics actually, as is, even blended. That's also make it hard. And also the conventional way, mechanical recycling, as I say, it has to be very clean. Means if you have many use, also the plastic polymer chopped off and I kind of downgrade it. So that's difficult to reuse many times. And also need to make it viable, need an economic driver. So that's the background here. Okay, so as the national lab, I'm the polymer scientist. We didn't work on this plastic recycling until probably this moment. So until DOE got really interested. So we had a workshop. So my former boss, Phil Britt, probably some people know here. He was the chair of this workshop, the report for the basic energy science roundtable on chemical upcycling polymers. So they identify what the challenges, and because actually Phil, I was kind of helping behind the scene on this workshop, document those things. So this is happened in 2019, and that's around the time we start. Many people in the DOE system start working on plastic recycling. So my title says upcycling. What is upcycling? This is a little bit joke on the picture here. The Wimbrath gave me this picture. This is the upcycle store in somewhere in the Amsterdam, but it was some bike shop or something like that. But upcycling means is to not just simple recycling. Is to make products with greater value. So most of recycling tend to go more downcycling, means if you reuse many times, it's not as useful as before. But we like to make it better than starting material, starting plastic, for example. So that's what we are trying to do on upcycling. Okay, just one review paper we wrote. There's challenges to make it happen. So especially, we are trying to work on sort of academic way in the national lab university to make a new product or new technologies. Industry does for kind of long time certain ways, more to mechanical recycling. Even new technology tend to be they developed maybe 20 years ago. So really bridging gap. That's a challenge. So we wrote a review paper. Actually, this review paper was chosen for the best review paper by the journal. So we are aware of these challenges, and we like to tackle these challenges too. Okay, so I'm gonna go more deep in research, a little more chemistry, but hopefully I can explain a little bit what's going on. So the polymer upcycling, plastic upcycling, we are approaching two ways. One is to existing this polymer, so plastic, to modify it to make it better. I'll show you two examples. Other way is existing polymer, but depolymerize, so deconstruct, chopping off to make it used for starting materials, then try to make some new materials. That's what we are looking at. So I'm going to go over the polymer, so modifying polymer. And, okay. So one of the things we start looking at is the cross-linked polymer, means it's network polymers. That's used many places, but once you network, typically you cannot recycle. It's a lock. You cannot reprocess. But now we can use new chemistry, and we can kind of swap it and we can process it. So that's important, make it recyclable. So we start this project. I'm going to show one more slide on the little more detailed mechanism. So the concept which was coined by the French group, Reaper. This is again, network, but that's dynamically exchange. So the properties like network polymer, so it's cross-linked polymer, but you can process like thermoplastics. So that means you can recycle. Also, there's solvent resistant, those things. There's several advantages of this kind of thing. So we start looking at this approach to existing plastic, but we can make it more higher property, but also recyclable. So that's what we start looking at this way. So one of the examples I'm going to show is we start looking at the thermoplastic elastomer. Thermoplastic elastomer is this kind of, so they something rubbery, but it's kind of tough materials. For example, the grip of the car handle too, but also the shoe sole, those things, or maybe some of the hoses, or maybe okay, everybody use probably every day. Toothbrush, this kind of little soft part, as well as the pen, this grip, this is thermoplastic elastomer. So can we make it more stronger materials using this, and also still make it recyclable? So can we make it this bitrimer from this? So one of the typical materials is SEBS, styrene ethylene butyrene styrene, tri-block polymers. Can we modify it, make it stronger, tougher, solvent resistance, and also still we can recycle. Also maybe the adhesion. So that's we are start looking at this kind of materials. So this is a little more the chemistry, but what we look at existing is plastic, thermoplastic elastomer. So the typical materials like this. We did one-step functionalizations. So this is the boron ester functionalizations. And what we found out, initial expectation was to cross-link with this, but we can cross-link with silicon nanoparticle. So this boron ester exchange, and you can make a bridge. So that's make a very useful materials. I'm gonna go a little bit more detail. So these are some evidence of NMR to see this is change, this is the IR to change. But I'd like to show one thing. This is the picture showing maybe a little bit dark, but on the right-hand side, this is not functional. So starting materials, silicon nano, this is with a silicon nanoparticle. It doesn't disperse that well. So actually, they don't like each other. But once you functionalize, it have interactions. And then once it dry, it's nicely dispersed silicon nanoparticle. But why are you saying this is bridged, chemically bridged? We have evidence. When you mix this boron ester, small molecule, with silicon nanoparticle, from NMR, it's shifted. Also, we did DFT calculation. So that what it means is we calculated binding this the interaction energies. So this has about this interaction boron and silica hydroxyl about 72 kilojoule. Means is it's not as strong as chemical bond, but it's much stronger than most of the secondary interaction. So it means is if it's hydrogen bonding, this is 10 kilojoule. So this is much stronger than that. So that's a strong evidence that's happening, bonding happening there. So, okay, utilizing that, so again, it's a little bit more detail, but this is starting material. So the thermoplastic elastomer is kind of elongated. So this is looking at strength, stress, and strain. Typically very stretchy materials. That's making it kind of tough. So toughness, it comes from how much this area. We functionalize it, and then adding silicon nanoparticle, making much better materials. So this is also modular strand here. And so another things we noticed is this is from DMA curve, this temperature. It's showing here this useful temperature. Starting materials like this range. This is a useful range because once you go higher temperature, it's kind of slow. So what's showing here between this and this, so that area, so about extension of 100 C extension useful range. So that's what happened. One thing. But then okay, this is also toughness on this one. But this is if this is N, this is just a little better, stronger materials. So this is the also the evidence on the solvent resistance. So the initial this polymer, it was soluble in many of solvent. Now it's not soluble. It's cross-linked network. So some applications, if you want to use in a solvent, this can be used. So that's something we did. But then most sorry, this is one more slide. Okay, this is the recyclability. So it's network. Traditional material networks, you cannot recycle it, but you can chop it off, you can press again, you can recycle it. This is showing similar mechanical properties. You can maintain it. So that's what you see. Multi-cycles, we can recycle mechanical way. But most interesting part is actually coming from adhesions. So you can actually stick very nicely. So this is actually semi-accidental we found because this time now he's staff member at so Anis Roman, he was doing this one on the glass. He told me he cannot take it out. It sticks so strong. So we start looking at the adhesion properties. This is again before doing this is starting materials. We functionalize it. This is a little bit up and then goes with nanoparticles addition. It's got much stronger. This is strength and also this lack of debonding. So showing here picture. So this is about 1 centimeter area. Actually, once that area can hang more than most 300 pounds or something like that. But with this, you can see it can hang very nicely. We apply heat and sticking. So that was something interesting we found using this. So as I mentioned initially, we couldn't take it out from glass. We did the same test. So this is again, this value is higher the better. But when you have this nanoparticle addition, this actually breaks. Glass breaks before this adhesion. So that's how strong it is. So what we have to do, we have to minimize area. So much smaller area, that's when can take the force, and then you can measure it. So that's pretty strong. Another thing, this is you can recycle. So even if you stick it, if you apply heat, you can take it off, you can put it again. What you're seeing here, starting materials, do it again, do it again, do it again. You can reuse it. Most of our heats right now, you cannot reuse. You just stick it, done. It's pretty difficult to reuse. So this is showing, because of chemistry, it's showing it. Also a little bit more detail. This is the calculation of interaction energy. So glass is silicon hydroxide. This the oxide group on there. So that's is higher than aluminum or the iron. So that's the showing there. So this is semi-summary of the adhesion properties. So this works as nicely adhesions. So look at this is the property here. Compare with super glue, epoxy, gorilla glue, elmer glue. These are the values: aluminum, steel, and glass. Glass is the highest, of course. Then, and in addition to that, can be recycled. This is quite useful. And also we did. I had one slide kind of talking about extended temperature range to be used. This is when you go 95 C temperature. This is still pretty high. This is our data. Compared with these commercial things, tend to go kind of become soft. So that's quite useful even high temperature on these materials. So this was okay. So this was highlight some of user articles and so this is so again, it's very strong adhesions, but you can recycle and we can reuse it. Starting from potentially from plastic waste, we can use that. Just one slide, similar chemistry was used for the composite. And it's actually almost same polymer as a little bit tweaked, but used for carbon fiber composite. This is currently right now composite is not recycled. We can make it recyclable, but quite tough. This is also featured by several articles as well. So we developed technologies. So this is actually just happened pretty much last week or 2 weeks ago. So both this adhesion and also combined with composite of this chemistry, but just right now the research licensed by Creighton. It's not publicly announced yet, but I think it's fine. This is known knowledge. So so this is hopefully they can commercialize this kind of technologies that's happened here. Let me move on to additive manufacturing. I know you will, Amy is coming next month, but chemistry what we use on the ABS on additive manufacturing. So additive manufacturing, 3D printing, you can print interesting shape. So the advantage of 3D printing, when you design something, you can do it pretty quickly. So that's the process of the manufacturing is much shorter. Sometimes with design to finish, it takes quite a long time. So these most common filament, this resins, is ABS, acrylonitrile butadiene styrene. This is the material for Lego. So if you don't want to melt it, but if you melt the Lego, you can print it. So for example, our famous Chevy Cobra, that was printed ABS mixed with carbon fiber to be printed. Keyboard, ping pong board, that's also ABS. So this is most common ABS materials. Can we make it better materials and also still printables that we looked at? So we did same chemistry I mentioned at Bitrimmer. We kind of make a network, but still make it processable. So that's we looked at. Little more chemistry details. This is two-step synthesis, but make it kind of semi-simpler. We add this one. This is the toluene chemistry. So this 18% more of butadiene. So this double bond can react. Added amine here, and amine can cross-link. In this case, glutaraldehyde. But this cross-link, this is the reaction can exchange back and forth. Even though it's network, normally network cannot be processed, but you can process. So that's we design. Some also color change happens. So you can see that. This is some of the IR result. So again, this is the tensile curves showing strain versus stress. So the stronger material goes much higher strengths, but so overall, actually, you want to have bigger area to make it tougher materials. Starting materials is the ABS need, like this. Once it crossing, so this ALD 33% amines crosslink. That's what it means. So this is a trend showing starting materials toughness to go up here. So in this case, we vary the ratios, different ratio on the crosslinks, and it's 33%. This was the best ratio, and we stick to use that. So this goes starting from 25 megapascal here to 45 or 40 megapascal. So it's pretty much twice stronger materials we made using this, and also tougher materials. Then this one, again, it's network formed, but you can process again. So you can recycle many times. So showing here some of DMA, also some of rheology, those things too. But this indicates it's reprocessable, but also actually indicate reprintable with this range. So printing. So printing first, we have kind of resin there. We make, hopefully video works. Yes. So you make a filament. The filament of this kind of filament, but you see extrusion here. And then making that, so this brown one is the one, our product, and then we can print. Printing is this normal resin, but you can see, you can print it for any design, you can print. And I think you can work there, I'm not sure. Okay, well, and then we wanted to compare the direction. So transverse direction is this way, longitudinal directions. And ideally, there's no difference, but this is typically there's difference. Again, neat materials, this is the commercial ABS. And our ALD30 is because the crosslink is networked. It's much, much stronger, about twice better. And also much smoother interface. So this actually interface is typically weakness of 3D printing. When you have a layer by layer, that's the weakness comes from. But it's much smoother, so that's much better. So that's we are able to do it. But interesting part is we can print many times. So we grind it, we can print, even some blended, we can do that. So you can see some of the things kind of neat materials kind of doesn't have a color. You can see a little bit blended. You can print many times. This is still one of the only materials you can print many times with this kind of chemistry we have. So that's something quite unique materials. Also, 3D printing give an advantage. So we are looking at some literature. Can we print something interesting shape? So beetles, forewing has nice structure to resist compressive. So if you push it down, they can resist it. This kind of honeycomb structure make it much stronger by weight to resist compressions. This is kind of curved here. And what you're showing here, normal ABS is like here. Even neat material, if you print this way, it makes much better. But ours this is as good as the composite materials. So that's how stronger we can make. So additional materials with also shape can make much more strong materials. Also, this is not soluble. So again, it's cross-linked. Original material is nicely soluble to solvent. It can dissolve. This is not. So we had an idea, what if we have mixture of plastics? So styrofoam, neat ABS, ABS bitumen, this is our product. You mix it, we can separate it out. So everything else is off, but this stays. So we can recover. So that's something, the pathway, we can recycle this kind of materials too. So again, this was a highlight of some news articles, and so Sonjin did this work, and he is now the assistant professor at University of Mexico. So we've done this. Where we are moving from this one is not licensed yet. We are looking for some licensee, but we are still looking at some actual industrial product. So this is the one example. This is carbon fiber ABS composite. It's quite common to be used for cars and those things. Kind of grind it, but we can recover it, we can upcycle it, and then we can print many. That's what we are trying right now on this kind of approach. I'd like to switch a gear to existing plastic, deconstructed to useful monomer or chemistry. That's I'd like to explain. That's an exciting work we have. So this project, it's a part of the basic energy science project. We are looking at fundamental science of this deconstruction. So existing, especially the condensation polymer, which means that the PET, nylon, polyurethane type of things to depolymerize, really control weight, and also using that building block to upcycle it. And one signature, okay, it's a little hidden there, but the Arif, he's here. He did excellent work. So we developed exciting and excellent catalyst. This is the best catalyst right now. Although it's simple, this is the strong base, this mixture TBD-TFA, nicely mixed. This is much more efficient to existing. So this case is PET, so plastic bottle materials. We can cook it, and then you can be the ethylene glycolysis. So conventional materials, you require much more materials. It takes much longer, higher temperature. Now it's only 5% more, around 180 C, 2 hours, you get quite high yield. There's a comparison a little bit more detail. So this is our catalyst. This is TBD MSA, was known to be the best before our publications. TBD is also this one. And we also fundamentally looking at the information of the importance of this hydrogen here. This massive methylated is not as good. But showing here in the picture, after 2 hours, nice and clear. If it's using this, I guess the best material before our publications was still 60% conversion. So nicely used, this catalyst is very effective with all the same conditions we use. This is some computations, but this maybe may not go down much detail, but we did combine DFT and emit simulations. But showing here, based on calculations, so this transition step, means it's lower. So this is much more efficient this hours versus some of the previous system. So that's we are showing here on the calculations. So this kind of indicates the plausible mechanism for this depolymerizations. More importantly, this can work many different plastics. So I showed the data of PET. This is the water bottle. This works for polycarbonate, like safety goggles, polyurethane, nylon, all of them. So far, this is the only catalyst really works well for all of them. And also the beauty is temperature is actually different. So polycarbonate is easiest to depolymerize. It happens at 130 C, almost the full convergence. Polyurethane is next, this red one. Next is PET. Then nylon comes. because of this temperature difference, if you have mixture of this, mixture of this, so this we have everything mixed, even the commercial product, we can do one by one, kind of cascaded way. So if you have 130 C, only polycarbonate depolymerized, this is the product you can get. 160 C is urethane and also the PET comes out a little bit. 180 C now, the PET comes out. This is the nylon still same. So if you want to separate, actually separation is a challenge for any of the mixture plastic. You can kind of like stay there. You can separate here. Then 210, you get these materials, nylon out, and also the 210. Everything mixed. Also, we can do that too. So that's show the process. Even if you mixture of these 4 different plastics, we can sequentially depolymerize. You can take it out. This is kind of recyclability. It's important, practically important. These are the catalysts, same catalyst can be used many times. Also, even with the water presence, this works. Some more detail. This is kinetic curves, so this doesn't change that much. So that's showing here. In this case, this PET. So what's the practical material? So we tried. I've tried all of the materials. So PET bottle. There's a video here. So this is glycolysis. It's actually not soluble. So as it goes, it's depolymerized, becomes soluble, and you can crush out later on the crystal out. So this is the starting material of the very useful chemicals you can get out. So that's all the process like this, quite similar. And we've done carpet, polyester carpet, cloth, polyester cloth, and a safety goggles. Also the polyurethane foam, and also nylon rope. So all of them works. So these are the commercial product. It works, and we did even more mixtures. So this case polyester cotton mixture. Actually, cotton is inert. It doesn't do much. It's kind of we can separate it out, so we can recover 100%. If you have contaminated plastic bag, it's fine too. We can do also depolymerizations, and then we can get back out. For example, the cap. This is a polypropylene. This is inert also this case, but everything else can separate it out, and then you can get the cap. So this means most of the plastic mixture we can deal with it. So that's our technology we have. Another thing, we did calculation of the greenhouse gas emission and also energy consumption. This is the same plastic. If you reproduce, starting from our process so waste is starting point. If you reuse this process to produce this monomer to make the same plastic, this is our data. Greens, this is our data, versus conventional way from petroleum. So this significant reduction. So about 75%, 95% reduction. Greenhouse gas emissions, also energy consumption is similar. So this indicates if its waste becomes a resource, and if you reuse it to reproduce similar kind of plastic, becomes really circular, and we can utilize that. So again, this was highlighted in the many news articles. Credit to Arif, and so this we have covered in journal cover, and also selected many of them by journal too. And this one, so there's a nice program in DOE. There's Energy I-Core. Knowing we have interest in technologies, so we attend this. As Energy I-Core teaches us how to commercialize, so lab-based technology, how to commercialize it. So we did. So I was the PI. Arif and Jackie was the entrepreneur lead, and then also the Gary was the kind of like advisory for these activities. So we did interview many customers, potential customers. We try to understand the market. This was very helpful. We'd like to thank DOE for this one too, opportunity. And then the Arif, again, he's here in the audience. So we or he founded company, we do, 2023. And he was selected by maybe people familiar with Innovation Crossroads. This is the incubation program and the Oak Ridge National Lab has. So he was selected for the cohort 2023. So he is now the startup company. Right now still one person, but we are trying to really commercialize these technologies. About this redo, so based on these technologies I just showed, this technology can treat many mixture of plastics, and also we can tackle many existing also plastic previously cannot tackle. So that's looking at by the redo right now. And also because the innovation crossroads system, I'm the owner of PI, and then of course Arif is the founder and CEO of the process. So again, all the activity we've done, basic science research to this commercialization, try to learn these things was very helpful. So hopefully eventually in a couple of years, we'd like to see actually plants build, and then we can treat many of plastics. So that's we like to do. Of course, he's here today, but if you have any questions, you can look at also his website too, but you can contact him. Okay, just a few more slides. What's research-wise going on? So I showed something to existing plastics to going down, but we are looking at to make a new plastics from that. So just one example, we already published this one. So Jeff, so here, Jeff done. So quite similar chemistry, same catalyst, but we made this double bond. That's make it new polymer we make, but this is nicely, you can go back, depolymerize a different mechanism. So something like that we can use for plastic we are making as a research. So that's this kind of activity going on. So hopefully in a couple of years, we have something quite interesting, new plastic we are making, which has a really circularity, so we can recycle very easily and we can reuse many, many times. Something else related to also sustainability. Start. Yeah, so we've been working on self-heatable polymers, so self-heatable plastics. I'll show the video here. That's very the more explaining. So when you have a damage, like cut, but you're seeing here, even after 5 minutes, if you have contact, that can already heal. So this kind of materials is quite useful. I'm going to show the sealant, the example, but let's start this one too. So you can see it's already healed, right? The other one also kind of you can see. So this is useful in a sense on some of the material choice. It could be car too, but one of the things we got attraction is the sealant. So sealant everywhere in the building, right? It could be bathroom, those things too. So the energy saving actually comes from a lot more like a replacement labor and as well as also energy. If you doesn't need to replace it, you can stay for a long time. So this is we developed a sealant, you can self-heal. So it's heal, even if damage happened, it heal itself. Right now we are working on this commercialization as well. So that's something, not only just simple changing recycling method, but this is making longevity of the materials. This is also important to address. Similarly, we've done the self-healing of thermal insulation materials. This is vacuum insulation materials. The vacuum insulation panel, this is this looks like this. This is the most effective thermal insulation. So this is the same performance, how thick it is. The polyurethane foam, this is glass fiber, this VIP can be very thin. But the weakness of this is somebody damage it inside its vacuum, it's lose performance. So we made this barrier film, this film here can heal. Even damage happens, it's healing. So this was last November, was licensed by Flexcon. So we are working together to commercialize. So again, we try to tackle not just upcycling, but also we are looking at different ways to polymer science to tackle this kind of to make it much more sustainable materials. So we are looking at. So I think that's it. So I covered 3 major examples. 2 example polymer to polymer. One is to adhesive. One is to the 3D printing, additive manufacturing. And third one is to depolymerize mixture of plastic. We can depolymerize useful chemicals and you can reuse it. So that's shown as an example. But we're gonna continue to work on. So hopefully, in a couple of years, probably we'll have something more. So maybe I can come back and talk about it. Yeah. So many of the work we've done with the exciting team. So the additive work is done. So at that time, as he was a postdoc with the Ernest Roman, he's done. He's continued to do that kind of work. Additive manufacturing one done by Sunjin. Now he's an assistant professor at University of New Mexico. And also the construction one is Eric. He's an audience. Again, he is now the startup company we use as CEO. And just one example I showed, but also Jeff's work, we showed that many other people also involved. So we'd like to thank, as well as also, of course, the funding for the LDLD, BS material science as well. With that, I'd like to thank you for attention. I'd like to take questions. Thank you.
Questions, speaker? Dave.
Have you done a full economic analysis, starting on the one side, a barrel of oil, and on the other side, a truckload of plastic bottles you would have to pay for, and eventually get to the same product for a kilogram of whatever plastic you would get to?
Very good question. So we haven't done full analysis, but we learned during energy ICO, waste should not travel too far. That's actually one of the major costs. So collection side collects plastic waste. If you can treat close to that, it's economical. But if you have to travel from coast to coast, it's not. So that's something we need to closely look. We like to recycle in Tennessee. So we haven't done full scale analysis, but we know it's profitable. Some other examples exist. Some other companies doing it too. So how profitable, we don't know yet. But if a system is built in the correct direction, distance, as well as also the ecosystem, it should work.
Ellen?
Does industry object to this material being too good?
Interesting question. I'm sure we got a lot of contact and there's a lot of interest, but some competitor, I know they have similar technology, but we know, I think ours is better. So I don't know. We didn't directly ask their opinion, but we like, so in our minds, we like Eric that we do to grow and then not take over, maybe different way, but I think it's something we like to address, something they cannot address right now.
So you mentioned that you have a method for recycling carbon fiber composites,
Yeah.
correct?
Yeah.
Is that something the automobile industry would be interested in?
Yes. So we've been working. I didn't talk about much. Just one slide I had, but we've been working on that too. So the lightweight vehicle that saves fuel and those things, that's a general interest. Right now, still cost is a little high, right? To use those composites. And those materials right now, it's not really recycled. So we are trying to make it recycled. So there's general interest, but I think vehicle company, they are watching right now. And I think we need to advance even more. Also make it cost effective. That's where we are.
Back there.
Hi. For those of us who are kind of more like me on the casual end of chemistry, and you go online to kind of just find out interesting science bits, there's a YouTube trend of something called piranha fluid, which is basically this very, very powerful solvent that people, science, chemistry teachers illustrate how cool sciences by dropping stuff into it and it dissolves like chicken, chicken legs and things like that. And the reason why I bring it up is that I remember learning that this fluid, I can't remember what the actual name of it is other than the colloquial one, would be extremely useful for breaking down plastics so that you could recycle it, but that it was considered too costly to use this chemical in order to do that. And I was curious whether or not that particular fluid was something that you were using to break down the, to do the initial taking of the plastics, especially the contaminated ones, put it in that so that it would all go ahead and break down so that you could scoop out the parts that you actually want to use in order to do this upcycling. If so, if that's something that, using this fluid and possibly being able to recycle it, clean it and then recycle it so that you could have like mini stations in different places so that the waste wouldn't have to travel, like having many places where you could just chuck the plastics into the thing, go ahead and break it down, and then turn it into whatever, whether or not that was something that Redo considered doing. If you're not using piranha fluid, what are you using in order to break it down? You might have explained, but I don't claim to be a chemist, so I didn't necessarily understand all of it. What are you using if you're not using that?
So we develop catalyst. So it comes down to selectivity. So if you are, I think it sounds like that system is just break down everything, but comes out 100 different things in there, then we cannot separate, we cannot use anything. So our system is very selective.
Okay.
So we can choose also different temperatures, we can take one thing out of the system. If you don't have this kind of selectivities, I don't think we can, industry can adapt. So in a sense, the strong acid or base can destroy everything. But then that mixed soup cannot use because everything mixed. So our system is make it really selective. We have target. We have to be aware, semi-aware what's in there, but we can kind of separate out different way. That's the kind of uniqueness about technology.
Okay.
Chuck.
Just about any activity has some process waste.
Yeah.
And my question is there any suggestion that you have production of nanoplastics, microplastics in the process of going through from the mixed waste to your chemically changed and improved plastic? Nanoplastic, the nanoplastic and microplastics in the environment are a big issue right now.
That's a hard question. So if you're asking, we put in our process, then that will take care of it, because if that's would depolymerize or separate it out. But if it's in environment, that's a little different kind of system. So that's, of course, somehow we can collect it. We put in our system, yeah, depolymerize, we can separate the useful chemical out. We can do that, but I think it's a different challenge in the microplastic in the environment.
But basically, you probably wouldn't, except at the initial collection phase where you have the mixed waste, you might produce some there in that grinding or whatever process you go through.
Yeah, typically I have to grind it. So yeah, that's possible. But I think it's process, I think can be built not to have that much sort of extra things or residue there. I think if you treat it all in the chemical process like we have, it will take care of it, all of them.
Good.
I kind of want to be last. This is loaded. My understanding is that they could have been making all these plastics from hemp and they would be biodegradable, but they outlawed hemp. so we couldn't do that. You have any,
So we actually, we work on the bio-based plastic too. So the potentially biodegradable. Challenge is performance or properties. Most of cases still not as good or as useful as existing plastic right now.
Yeah.
If you can, also cost. So if the cost is competitive, performance is ideally better, then that's of course, eventually, that's not as easy as we say. So we are looking at actually the bio-based building block, potentially biodegradable. We are looking at it, but that's another many years of research to be done, I think.
thank you.
Well, in case that's not the last question, others. Greg.
Are there other countries that are doing similar research? And are they keeping it private or are they making it public?
Good question. So it is global competitions. We know the player in the research area who is competitor. I think in general, we see Europe, they are a little bit ahead in general in plastic recycling because of policy and everything. They started earlier than US. US has high activity right now, so I think we're gonna generate many technologies. But then also the Asian country they are doing. So it's a global competitions. They're hiding or not, I don't know, but we have some sense where we stand. We can confidently say this is really good technologies. And actually, we got even global contacts. Some other country they contacted us those things too. But our challenge or to do is, of course, right now still kind of laboratory scale. We have good technologies. Can we really deploy? So this is now it's kind of like our job, but if we can really deploy in the system, maybe first US ecosystem, but later on maybe even internationally, that'd be great. But it is global competition.
Yeah, I have a question. This boronic acid method for linking silicon nanoparticles into plastics have you identified, besides the adhesive, killer app for that? And does the presence of these silicon nanoparticles create another recycling problem that also has to be solved?
So, okay, that's a good question. So boron, so far, boron ester system, in my opinion, actually adhesives, right now the best applications. That's why actually I create on license. They see the result is pretty good. Nanoparticle potentially issue, but good part is we can actually chemical recycle. We can cleave. If you put pinnacle with solvent, actually we can dissolve everything. We can actually recover.
So you can undo it.
Yes, we can do it. Although industrially they want to do that process, I don't know. But we have a solution for that. But I guess any nanoparticle or nano system, of course, if it's once it's mixed in, to removing it's always a challenge. There's a way for ours, but that's a good question to think about for the down the line, I think.
That I'd say let's thank our speaker.
Okay.